Okay, I'm going to apologize in advance. This is going to be a little bit of a long one. It's a big one in the AP curriculum. So we're going to talk about greenhouse effect. All right. So a greenhouse is basically it's a structure that humans build that's designed to let plants stay warm in the winter months by using basically passive solar. So the idea is the walls are made out of glass. Glass is a material that has the ability to let sunlight pass through without being warmed by it. The sunlight doesn't interact with it, and then it comes in and it will be absorbed by some things in the house. It will also allow plants to grow, but things in the house will warm up. Maybe it's water or furniture, whatever. But things in here will absorb that energy and turn it into thermal energy. And when things get warm, the atoms jiggle faster, and when things jiggle faster, they make infrared light. But here's the deal: that infrared light's not able to pass out through the glass. So whereas the glass let visible light in, it doesn't let infrared light out. It absorbs that infrared light. So the glass heats up and it jiggles. And when it jiggles, it makes infrared light, but it makes that infrared light re-radiate in all directions, half of which are out of there, but half of which are back in. So basically, what happens is half the energy that comes in doesn't go out directly. And so, as a consequence, the temperature warms up. And so, this is able to stay warmer than it would if the infrared light could just leave. And so, we call that a greenhouse mechanism. Well, it turns out the Earth operates on a similar thing. It has basically gases that act like the glass in a greenhouse that let visible light in but block the infrared light from leaving. So, the atmosphere is primarily composed of nitrogen and oxygen, N2 and O2. And these gases are not greenhouse gases because they let visible light through, doesn't interact with them just like the glass of a greenhouse, but they also let infrared out. So if that's all we had in our atmosphere, the world would be really, really cold. We wouldn't be warm. But the reason we're warm is because we do have these naturally occurring greenhouse gases. Now, the naturally occurring greenhouse gases are H2O, water, carbon dioxide, CO2, methane, CH4, produced by anaerobes, and N2O, nitrous oxide, which is produced by volcanic eruptions. And there's also another important one, which is CFCs. Now, these are purely made by humans. There's no natural equivalent of these, and College Board wants you to know that. Now, all of these collectively are known as greenhouse gases. Here's why. All of these ones let visible light through just like the glass of a greenhouse. But when infrared light interacts with them on the way out, they absorb that infrared light just like the glass of a greenhouse. They get hot, they wiggle, they make infrared light, which is re-radiated in all directions, half of which bring them back to the ground. And they keep the world warm. Now, most of you have probably noticed this that water is a greenhouse gas because clouds are made out of water. So in the winter, you've probably noticed that the coldest nights are when there's no clouds overhead. These clear nights in the wintertime tend to get very cold. Why? Because infrared light in the ground is able to leave freely into space without being absorbed by the clouds. So that means the ground loses a lot of energy and gets cold, and the air near the ground gets cold as well. Remember, this leads to temperature inversions. Well, if there's clouds, what happens is that infrared light leaving makes the cloud absorbs it, warms up, and re-radiates that in both directions. Some of it gets radiated into space, but some of it gets radiated back down to the ground. So it slows down the rate at which the ground cools. And so over the course of the night, it doesn't get as cold. It's the greenhouse effect. And so most of us have noticed that, okay? Well, here's the thing about water vapor, though. It's not really considered to be an important greenhouse gas, and the reason is because it doesn't accumulate in the atmosphere. There's a fixed amount. The water cycle keeps moving in and out of the atmosphere. So, anytime you get too much of it in the atmosphere, it just starts to precipitate out. So it doesn't have an ability to reside for long periods of time. So it doesn't build up over time. And so we really don't really consider it when we talk about greenhouse gas. We mostly just use it as a way of pointing out about cloudy nights and clear nights. Carbon dioxide is a different matter, though. Carbon dioxide is a big contender. So CO2 is very good at catching infrared light and converting it into thermal energy and radiating it as infrared. And here's the deal. Over the course of the last century and a half, during the Industrial Revolution, we have just taken tons and tons and tons of fossil fuels out of the ground, burned them, and dumped the carbon dioxide into the atmosphere. So this yellow line shows that in the last century, we've gone from about 290 ppm carbon dioxide to over 400. Consequently, the temperatures have gone up along with that because it basically acts like a greenhouse gas. But it's not the only greenhouse gas. But I point out carbon dioxide first, and here's why. We use it to assign what are called GWP numbers. So a GWP number means global warming potential. And it turns out that different molecules have a different ability to capture infrared light and turn it back into heat. So CO2, being the main component that causes global warming, is arbitrarily assigned a GWP value of 1. All right. Now, methane, which is the second most largest contributor to the global warming problem we're facing, has a GWP of 28. What that means is it takes like 28 molecules of carbon dioxide to equal the effect of 1 molecule of methane. That's pretty significant. Now, it turns out we dump a lot more than 28 times more carbon dioxide in the atmosphere than we do methane, but the point is, methane is 28 times better at turning infrared light into heat than carbon dioxide is. Nitrous oxide is basically 10 times as powerful as methane with a GWP of 265. And CFCs, which remember these are artificial, these ones are in the thousands. Okay, and there's a lot of different ones of these, but they tend to be over 3,000, maybe even over 4,000. Well, let's talk about carbon dioxide. As I said, it's really what this show is all about. Okay, so carbon dioxide is the largest contributor, even though it's the weakest at capturing infrared light, has the lowest GWP of all the gas we talked about. But the deal is, we burn a lot of stuff on this planet. Remember, like over 80% of the energy we use on this planet comes from burning coal, oil, and natural gas. And when we burn these things, we always produce carbon dioxide. There's no way to burn fossil fuels without making carbon dioxide. And we burn a lot of them. So there's a lot of carbon dioxide, and it has a long residency time in the atmosphere. And we'll talk in a later one about how the carbon cycle affects it. But the bottom line is, it's really building up a lot. And as a consequence of that, we're seeing changes in temperature. So essentially, we're taking carbon that has been sequestered, buried underground, for millions, tens of millions, hundreds of millions of years. It used to be in the air way back when. Photosynthesis took it out, and then instead of cycling it, it got buried underground and sequestered for all that time. And in the last 100 years, we've just been digging down, digging up, and releasing in the atmosphere. And we shouldn't be surprised that we've seen a change both in the chemistry of the atmosphere and in the temperature of the atmosphere. Now, methane, CH4, is the second biggest contributor to global warming. Now, it's produced in many ways, and you should know each of these. So one way is by fracking. So remember, like when we fracked these shale deposits to release the gases in them, a lot of it just leaks out of the ground. Remember, there's one picture of a person's water in their sink was catching on fire from all the methane trapped inside it. Also, too, it's just any oil well. Like when we dig oil wells, typically one of the components of a petroleum deposit is methane, and so often that just leaks out of the ground when we dig oil wells. Another place is they're produced by animals, like ungulate animals, like things that eat grass and leaves. Cows are the biggest of this, though. So cows, you recall, they can't they eat grass, which has a lot of cellulose, but they can't directly eat the cellulose themselves. So instead, what they do is they have a symbiotic relationship with these anaerobic bacteria in their gut, and these anaerobic bacteria basically digest the cellulose into a form that cow can then itself digest. But anaerobic bacteria are known for generating methane. And so the cows just had to belch out all this methane constantly because people like cows. They like to eat cows. There's a lot of cows on the planet, and the cattle industry puts a lot of methane into the atmosphere. Another large source of methane in the atmosphere, as you recall, is landfills. Again, it has to do with anaerobes. So in a landfill, the aerobic bacteria quickly suffocate, but those anaerobes keep digesting the food, albeit slowly, but they generate methane over time. And you have to do something with it because it builds up. So you either vent it or you got to do something with it. And another place it's coming from, we'll talk about this at a later presentation, is the melting of the frozen ground, or the permafrost in the Arctic. So there's anaerobes had made methane, but it got frozen, and as that frozen land melts, then it gets released into the atmosphere, and that's becoming a more significant source all the time. Now, when we talked about landfills, we talked about methane, but that was before we talked about energy and electrical production. So let's just bring them together. So look at what a lot of municipalities are doing now. So it makes a lot of sense. You take a landfill, it's going to generate methane because anaerobic bacteria are going to eat your trash. If you collect that methane, you could just release it in the atmosphere. But remember, every molecule you release is equal to 28 carbon dioxides. But wouldn't it make more sense than to pump it over, clean it up, and then burn it? Make steam turns a turbine turns a generator, makes electricity, right? Why not? Well, remember, anytime you burn a hydrocarbon, you're going to end up making carbon dioxide. But it makes sense, and here's why, if you think in terms of GWPs. So here's a balanced chemical equation for the burning of methane. 1 molecule of methane plus 2 molecules of oxygen make 1 molecule of carbon dioxide and 2 molecules of water. Look what you've done. You've reduced the global warming potential by a factor of 28 because you took this one has a GWP of 28, this has a GWP of 1. So it makes a lot of sense to do this. Now, another place we get global warming from is nitrous oxide, N2O. We get this from burning fossil fuels. If you recall, in the engines of cars and in coal burning power plants and oil burning power plants, we have very high temperatures. And those high temperatures, nitrogen combines with oxygen. It's just an unintended consequence of that. And so we do release a bit of it that way. It also gets released by fertilizers and cow manure, human sewage, of which there's also quite a bit of. CFCs in College Board, once you know, that's the one artificial, completely artificial uh, um, greenhouse gas. They have very high values, like in the thousands, right? But the good news is that we don't really use them for refrigerators and air conditioners and spray cans and the production of foams anymore. So we used to do that, and it was really bad. Now you should remember that global warming and ozone depletion are two totally separate things. One molecule contributes to both of those, but the effects are separate from each other. Now, so let's just, if we think about it, it's CO2 levels have been pretty steady throughout the geologic past. Sometimes they go up, sometimes they go down. For most of human history, they've been just a little bit under 300, and the Industrial Revolution changed all that. But 300 is nothing to sneeze at. It's still a significant amount. I mean, we're talking like 1/3 of 1%, but still, that is enough to do something very important. Without that, if it was just nitrogen oxygen, the world would be like negative 18 degrees Celsius. We need to trap the heat, and carbon dioxide does that because there is that small amount, that 300 parts per million of CO2. That's what keeps us at around 15 degrees, where we would be at negative 18. So thank you, carbon dioxide. You're a very wonderful thing for our planet. It would be hard to have life here without you. But the problem is, too much of you is too much. Now, one of the things you're going to be asked to be able to analyze on your test in May is energy budget diagram, and they can be a little bit tricky. So let's just look at this for a second. So we got to keep in mind there's two different things that can happen to energy coming from the sun. It can reflect into space or get absorbed by either the Earth or clouds or greenhouse gas. Now, the idea is that we'll say we have 100 units of incoming energy from the sun. Albedo is basically reflection. So albedo is, well, what portion of that incoming light bounced away into space without ever getting absorbed? And so what can it bounce off of? Well, it turns out about 25% of the incoming light just bounces off clouds. They're white. If you look at them from above, they're white. That means light's bouncing off them into space without getting absorbed by the clouds. About 5% of it is bouncing off Earth's surface, off snow, off sand, off shiny surfaces, okay? So that's what, that's like 30%. Okay. Now of the remaining 70%, about 20% of it gets absorbed by clouds, and about 50% of it gets absorbed by the ground. All right. So now what happens? Okay. So if it gets absorbed, it's going to generate infrared light. Okay. So what happens is as we send infrared light into space, now we'll get this number 120 in just a second, but right now, so basically, we're going to end up sending 120 units radiating into space. Now, of these 120 units, they're going to get captured by greenhouse gases primarily, and remember that's going to radiate them in both directions. So that means of the 120, half of it, 60, is going to go into space, half of it, 60, is going to come back down to the ground. The clouds are going to absorb, remember, 20% of the energy coming in from the sun, and they're going to radiate half of that as infrared into the space upwards and half of that downward. So that 20 gives me 10. So this 10 plus this 60 is 70 units coming into the ground, plus 50 units coming directly in from the sun. 50 plus 70 is 120. So that's the cycle we've got. Now what we'll notice is basically if we do our math, what we'll see is that the total energy here works out to be, all the energy in equals all the energy out for the most part. And what happens is tiny little changes in the amounts of greenhouse gas make all the difference in the overall temperature of the atmosphere. So I just got ahead of us here, and so I explained this one here. So I'm going to keep going. Now, when the world is at what we call thermal equilibrium, that means the energy in equals the energy out, then the temperature of the atmosphere stays constant. Now, it never really does that. It's never really in thermal equilibrium for any significant amount of time. But if it is, then the temperature will stay constant. What we notice is that the temperature of the Earth's atmosphere has changed quite a bit over time, and we'll talk about in a minute how we know that. But basically, what happens is this: when greenhouse gases and albedo increase, uh, when when albedo, I got this backwards. This is supposed to say decrease. I can't believe I did this. Okay, so when you have more greenhouse gases and less albedo, then the temperature is going to go up. And when you have less greenhouse gases and more albedo, then the temperature is going to go down. And I'll fix this for the presentation. I apologize about that. Okay, so the bottom line is albedo keeps Earth from getting sunlight, but greenhouse gases make it absorb it. And so these two things change over time, right? So volcanic eruptions can put a lot of carbon dioxide in the atmosphere. A lot of snow can make a lot of albedo or volcanic eruptions. And as a consequence of that, we see over time there's been some significant changes in the overall temperature. This dashed line is basically what we consider to be normal prior to the Industrial Revolution, right? It's gone up since then, but before that it was colder, and we had an ice age. But there were times in the past where it was significantly colder than that, and times in the past when it was significantly warmer than that. Let's see why. Okay, I'm sorry. Let's see how we know that. Here's how we know that. Uh, we can determine what the CO2 levels were in the past, primarily by looking at ice cores in Antarctica and in Greenland. Greenland can take us back about 100,000 years. So there's ice at the bottom of those glaciers that's 100,000 years old. There's ice in Antarctica that's like 800,000 years old. When that snow came down to form these glaciers, it trapped the old atmosphere with it. And so we can analyze it to see, well, what was the percentage of carbon dioxide in the atmosphere way back then? It actually works. So we can take a core of this, just drill a hole and take it out, and then we can analyze it in a laboratory and just see what's the percentage of carbon dioxide at different depths. Okay, and we can also figure out what the temperature of the Earth was then, going back much farther. We can tell the temperature of the world going back almost to the dawn of time, and it's kind of interesting how we can do that. So I just want to talk a little bit about how it is that we're able to tell the temperature in the past. The carbon dioxide level, the only way we really get it, to be honest, is from ice cores. But we can use, I'm just going to look at this. We can use tree rings, we can use ice cores, we can use coral reefs, and we can use ocean sediments. And all of these can be used to tell us what was the temperature in the past. Let's just get on it. So tree rings. If you have a warm, wet season, trees grow fast, and what happens is this fast growth in a tree ring looks like this. It's very thick. So if we take a tree, cut it in half, we see this, right? But if we have a year where it was cold and trees couldn't grow much, the rings are much smaller. And so we can basically look at these rings and tell what the temperature was like compared to now in the past. Now, trees, you can go back about maybe 1 to 2,000 years with trees. And hopefully you don't chop them down when they're that old, you drill holes through them. But we can use tree cores as a way of determining what the temperature was going back 1 to 2,000 years. But oxygen isotopes are awesome. And let's just dig into these just a little bit. So here's the deal. We can use oxygen isotopes to going back a lot farther than that. Here's the deal. Most of the oxygen on the Earth is oxygen 16. Okay, if you remember from the periodic table, the atomic weight of the formula mass of oxygen is 16, right? 15.99, I believe. But a small percentage of it is oxygen 18, a heavy isotope with 2 extra neutrons. So if a water molecule is made with one of the atoms in it, or both the atoms, is O18, well, that's going to be heavy water. And so heavy water is not going to evaporate as easy as regular light water with O16. So the idea is a small fraction of the water in the ocean contains O18 instead of O16, and that makes it heavier and less likely to evaporate. Okay, and with that you can do magic. Okay, so take an ice core. We look at an ice core. Here's the deal. All right. If the temperatures on the planet are overall warm, then that means we're more likely to carry O18 out of the ocean and deposit. So when I look at an ice core, If I notice there's a lot of heavy water, 18, then I know temperatures must have been warm, and we can even equate them to how warm. And if I find there is an absence of 18, well, that means the temperatures were cold, and so we weren't able to evaporate as much of the 18, the heavier water. Ah, pretty cool, huh? All right. What about coral? Okay, well, here's the deal. So coral forms by making calcium carbonate. In order to do that, it's got to basically take some of the um, water out of some of the oxygen out of the water to do that. Okay, and so again, so the deal is, if the temperature is really warm, then that means that there is going to be less 18 in the water, so there's going to be less 18 in the coral. So when I find corals that have low amounts of 18, that tells me it must have been warm then. If I find corals that have a high amount of 18, that tells me it must have been colder back then. Even if these things are growing in tropical areas, overall the ocean's amount is going to vary depending on the overall temperatures. And the thing about corals is they're present in fossil records going back hundreds of millions of years. And then ocean sediments, we can go really far back. So it's the same deal here. So just like it's the same process that coral forms, that forms these coccoliths and foraminifers that are made out of calcium carbonate. So the same deal. If I see that the 18 level is low, that means it must have been warm because it's been evaporating. And if I see the levels are high, it must have been it was cold. Pretty cool that we can do that. Now look, by combining these paleo data, look what science has been able to find. So I use ice cores to look at the carbon dioxide levels trapped in the ice cores, and I get this pattern for the CO2 levels going back in time. Right? I use those other techniques, those isotopic techniques or tree ring techniques, and I look at what was the temperature in the past. I get this very high level of correlation here. It's remarkable level of correlation that we get. So what it tells us is carbon dioxide, whatever it does, that's what the temperature does. Now let's just look here. Here is the CO2 level going back a long time. Was that like 80 million years, I think? All right, and what we find is for all that time, the carbon dioxide levels have been pretty low. Right, the highest peak was at 300. Well, look at them now. They've never been this high before, guys. This is the highest we've ever seen the carbon dioxide levels. And what carbon dioxide does, temperature does. It might take a while, but it's doing it. And so that's why it's kind of frightening to people. So this is a graph that you'll definitely get very familiar with. So what happens is, as at Mauna Loa in the middle of the Pacific Ocean, we have a monitoring station where we monitor the atmosphere. And one of the things we clearly want to measure is carbon dioxide. And we get this pattern here. And we can see from 1955 to now, there's been this rapid increase like this. Now, it's kind of cool. These seasonal variations have to do with productivity, right? So when it's the summer, the Mauna Loa is in the northern hemisphere. So in the summertime, there's more productivity. So that means the carbon dioxide in the atmosphere goes down because there's a lot of photosynthesis. And in the winter, there's less photosynthesis, so the levels go up. That's why we get this wiggly pattern. They might ask you that on the test, actually. Now let's look at this graph here. Okay, so basically what we do here is we can use what's called an anomaly graph. An anomaly basically says, let's just take the midpoint of the last century or whatever we want and say, okay, we're going to call that 0. That's our 0 line, the midpoint. Okay, and we're going to see like was the temperature above or below that midpoint. And when we do that, oh my God, look at this. This is the graph that we get. Look at what's happening now. So basically, carbon dioxide levels were, the Industrial Revolution started about then. They slowly grew. And after World War II, they really picked up. And after the 1970s, it really picked up. And as the carbon dioxide levels have gone up, so has the temperature of our planet. It's just as clear as can be. Now, it's worth noting, of particular concern, is that it's not like the whole world. One of the reasons it's hard to say that global warming is happening, a lot of people want to deny it, is because there's weather. Weather is the day-to-day change. Climate is the long-term averages. Well, because it's like how you measure temperature varies from place to place, it can be kind of confusing. But if we look at how it changes in different latitudes, it's very dramatic. What we find is that when we're close to the equator, we don't really see a whole lot of change. But as we move towards the North Pole, what we find is the temperature anomaly goes up quite a bit. So the global warming is really something that's happening very rapidly at the North Pole, and it's causing the polar ice sheet there to melt. So guys, I'm sorry this one took so long. It took me 3 times to do this. I totally screwed up halfway through twice actually. Anyway, thank you for watching.